So let us start our seminar today with the speaker Dat To from Paris 6. He shall speak on the convergence of the Kähler-Ricci flow on variety of general type. Yes, please.
Yeah, so thank you very much for the invitation, and yeah, I'm very pleased to give a talk in the seminar. And maybe can I share the screen? Share screen. Open. Okay. Okay. So do you see my screen? Okay. So maybe I start. Okay. So today I would like to talk about. Do you hear me? Please just confirm.
Yes.
I can hear.
Go ahead, please.
Okay. Good. So today I would like to talk about my recent results on the convergence of the Kähler-Ricci flow on Kähler manifold of zero type. So it should be a projective manifold of zero type. And I will start with some notation on the Kähler-Ricci flow. So suppose X omega is a compact Kähler manifold. So omega is Kähler form, and we consider the Kähler-Ricci flow on X, which is an evolution equation of the one-one tensor. So the one-one form omega t, which is equal to minus Ricci omega t. So here, if you write down omega is locally by Ij k bar, then the Ricci can locally write down like minus DDC of determinant of the matrix J bar. So here I use the notation from the pluripotential theory, means DDC equals to I dd bar up to some constant. I mean maybe I dd bar divided by pi. Okay, so but
may I interrupt you? That means that the Kähler-Ricci flow is exactly Ricci flow, but for Kähler because everything agrees, so that is a normal Ricci flow, right?
Yeah, I will say about this in 1 second. Yeah, so this is exactly the Ricci flow of Hamilton when the manifold is Kähler. Okay, so that's a short word like this to introduction. So here, but I'm interested in the Kähler case. I mean, we have a lot of property from the complex Kähler manifold, and also some properties from the algebraic varieties. So here, if you take the cohomology class along the flow, I mean the Dunbar cohomology class, you can see that, of course, class of the metric omega t along the flow, we can write down like omega 0 plus t c1 kx. Here c1 kx is the first chance class of the canonical bundle. Okay, so if you take the cohomology class of omega t, the derivative of omega t with respect to t, you can see that it exactly is the derivative of the cohomology class omega t, and derivative of cohomology class of omega t, and the right hand side is exactly the c1 of kx. So you got the ODE equation for cohomology class. So from this you can imply that we have this formulation for the cohomology class along the flow. So here you can see that since omega 0 so is a Kähler matrix, C1 kx is a closed class, so omega t, I mean which should be closed form. So along the Kähler-Ricci flow, the omega t is always closed. So that's why we call this Kähler-Ricci flow, because the Kähler property is preserved along the flow. Okay. So for the existence time of the flow, so there is a famous result of the Hải Đông Cao and then Tian and Zhang say that the existence time for the smooth solution for the Kähler-Ricci flows is determined by Tm, which is subsumum of T positive, such that the class omega T is Kähler. I mean, if you can take some Kähler metric in this class. Okay, so this is the existing time. And then this time is infinite if and only if Kx is nef. So that means the first class of the calorical bundle is in the boundary of the Kähler cone. Kähler cone means the cone of all Kähler class. Okay, for this part. So Kx maybe not inside K, big capital K, but maybe in the boundary of the capital K. So it's a defect. So if Kx is ample, so metrically we can say that C1 Kx is a Kähler class. That means we can find a Kähler metric in this class. Then the cow shows that after normalization, the matrix will converge in C infinity to the unique Kähler-Einstein matrix. So here I make some mistake here. So this is really omega K E is a unique Kähler-Einstein matrix in C1 Kx. So that means the Ricci of omega K E is equal to minus omega K. So it gives the existence of the Kähler-Einstein matrix on a manifold with ample canonical bundle, line bundle. So sorry.
Can I ask a somewhat elementary question?
Yeah.
This condition on the existence time, you say that infinite existence time implies that this class has to be in a boundary of the Kähler cone? Do you mean the boundary or the closure?
It's the closure, because if
closure.
you take,
okay.
Here I take the closure.
Closure.
Because if C1 Kx is the Kähler, this it should be positive, so you can see that Tm is infinity, right?
Okay. Yes. Thank you.
So, but of course, it's true for the boundary of K as well. So I take K bar. I mean closure of K. Okay.
Okay. Thank you.
Okay. Thanks for the question. So here is the case ample. I mean C1 Kx is inside the cone. So the cone is open. So this case when Kx is ample, that means the C1 Kx is inside the boundary as the closed set kappa K. So we have the conversion results by Chow. And then another case is when X is Kähler-Bizarre manifold. So from this, we can see that, of course, the maximal time is infinity as well. And then without normalization, we can see that we can see that omega T will converge to Ricci flat matrix, Kähler-Ricci flat matrix. That means the Ricci of this matrix is 0. So this gives the existence of Kähler-Ricci flat matrix on Kähler-Bizarre manifold using the flow approach, Kähler-Ricci approach. Of course, this is the existence of the Kähler-Einstein matrix in the case of Kx is ample, already proved by Xing-Tung Zhao and Obang in 70. Okay, and the result of Zhao on 78. I mean, for the Ricci flat matrix existence, and then Cao in 85 use the Kähler-Ricci flow to recover the result of existence of Kähler-Einstein matrix in some special case. I mean, when C1 Kx is ample or Ricci or 0. Okay, so this is a very classical results of the convergence of the Kähler-Ricci flow when C on Kx is have a side positive or 0. So in particular, we have another convergence result with respect to the Ricci flow, where we have some weaker condition on the canonical bundle, line bundle. So here, let's say it is smooth minimal model of general type. That means the canonical bundle, line bundle is nef and big. So I will explain what is big, but easily that big, that means the codadar dimension of Kx is exactly n, the dimension of manifold. Or you can see that the volume of the first chance class of Kx is positive. Okay, so it's strictly positive is the thing of big. And F, I already explained in the last slide. And then Chuzi considers the Kähler-Ricci flow like this, starting from a Kähler matrix. And then he shows that the matrix exists for on time t, so it's already well known because, as I say that, the time existence is infinite, infinite if and only if Kx in F. But the main thing is that there exists a subvariety of codimension 1 S in X such that the normalization of the flow will converge to a Kähler-Ricci flow, Ricci Kähler-Einstein matrix defined on the complement of S, I mean the open Zariski S minus X minus S. Here the matrix omega k e satisfies the Ricci equation, Einstein equation, Ricci of omega ke equal to minus omega of ke on this open Zariski. Okay, so in the proof of Cow when Kx is ample, so ample implies that Kx in F is big. We have the conversion is on X, but if we have less information or weaker condition on Kx, we have the convergence, but in open Zariski. Okay, so it's for long time existence. We have another results with respect to the long time existence of the flow when Kx is not big, but I don't want to go further in the details. But just mention some names like Tozati, Wenkov, Songqian. What I was interested in is the kind of finite existence time. So that means the maximum existence times is finite. So let's X is a smooth projective manifold of zero type. That means Kx is only big. So not, we don't need to use only here, but I mean that the condition here that Kx is big. We don't need to add the condition nef inside. So here, because of Kx is only big, the maximal existence time is finite because it only big, not nef. So there is a result of Collins and Tozati. He say symbolize that the Kähler matrix, there exists a Kähler matrix on the open Zariski X, such that the Kähler-Ricci flow will converge to this matrix in this open Zariski in the C infinity no cone sense. When T approach the finite existence time. Okay, so that means the flow will develop some singularity when X approach the maximal existence time outside open Zariski set. Okay, so this very interesting result. And this result of Collins-Tosati response gives an answer for the question of Feldman-Ilmanen-Knopf in 2003 that the flow of Kähler-Ricci will develop some singularity at the maximum existence time outside a closed Zariski set. So is an answer for the one question of Feldman-Ilmanen-Knopf. But in Feldman-Ilmanen-Knopf paper, they propose several questions. And another question is the following. So we respect the same condition here. So Kx is big and X is manifold zero type. Can we define and construct the weak solutions for the Kähler-Ricci flow when T is bigger than the maximum existence times for the smooth solution? That means that we need to have some definition for weak solution, right? So because of when T is bigger than T maximum, Tm here, the solution would be singularity, to have some singularity, which is not smooth as well, but we have some kind of singularity. So we need to define the solution in weak sense. And this exactly my my goal today. So I just would like to mention some related works on this direction with Songxia, Novenkov, Tosati, Collins, and also Expedia, Zariski on this direction. And here I would like to mention my main result. So before this, I want to simplify the Kähler-Ricci equation, Kähler-Ricci flows in the case of Kähler manifold, and let theta is a one-one form, which is determined by taking IDD bar of some log of some volume form, smooth volume form, and which is an element in C1 Kx. And denoted by theta t, family of one class. So on forms defined by E minus t omega 0 plus 1 minus E minus t theta. Theta is this one form. Okay. So from this setting, we can see that using the DDC lemma. For compact Kähler manifold, we can see that in fact the normalized Kähler-Ricci flow can be written as a complex Monge-Ampère equation, complex Monge-Ampère parabolic equations, or I write here as a complex Monge-Ampère flow. So is this exactly theta plus DDC, so IDD bar of phi t to power n equal to e to power the derivatives of phi t respect to t plus phi t time with the volume form. So here's the left hand side. You can see that is so in the smooth case, which is a volume form. The right hand side is a volume form as well. So it's verified when you take the quotient of two volume forms for the density. Okay, and because when you take t equals 0, theta t is exactly omega 0, so the potential phi t here should be 0 at the beginning. Okay, so you can see that the solution of Ricci equation is exactly this form. So theta t plus DDC of phi t. So it is exactly omega t, the matrix along the Kähler-Ricci flow.
So that you say that the omega is a not volume form, but the density of the volume form, right? And then you can take log.
The
omega big is a
volume form. Yeah, is it a volume form?
So and when you take log, that means that you take the density, right?
Yeah. So this is a volume form, and this is volume form. So you take the quotient and you take log. So this is exactly a function. So it's the density, right?
Yeah.
Yeah. So this I mean that we write out in this case in terms of volume form, because after that we can define phi t in which sense? I mean, which is not smooth, but no longer smooth, but somehow have some similarity. So this should be a measure. Okay. After when we define Phi t is not smooth, but some PHK function, pluri-subharmonic function. So this should be measured, and so this more volume form. So we have something like well defined for the weak setting. Okay, for this part.
Thanks.
Okay, thanks for the question, because this is one of the key point why we write down the Kähler-Ricci flow in this formulation, because after that this is verified for the weak setting. Okay?
I see. So that's a ER trick.
Sorry.
So that means that the ER, how to say it, reformulation.
Yeah.
Right in this way, right?
Yeah, right. I would like to write down in this way. In the case when the Phi t is smooth, this so you can write down is like a determinant of the this form equal to this equation. So I think that. But when we have Phi t is not smooth, this kind of the measure, so it would be flexible to working on. Okay. Now I would like to start my main theorem. So let x omega 0 be a variety of zero type. So somehow I mix the term of Kähler manifold or something like the projective varieties here, because in this case we consider the case of Kx is big. So if Kx is big, so it's well known by the result of Moserons that the variety should be projective. So I remove the term of manifold, Kähler manifold, but add the term of variety. Okay, so let's x omega is a variety of zero type. Then the normalized Kähler-Ricci flow starting from omega 0 admits a unique viscosity solution, omega t equal to theta t plus ddc of phi t for on time, for on t positive. So here we have the term viscosity. So that means I will define our solution in a viscosity sense. So I will go back with this setting in 1 minute, in some seconds. But here I just want to state the theorem that in fact we can define the solution in some weak sense, and then this responds the question of Feldman-Ilmanen-Knopf that of course in some way you can define the weak solution. And moreover, I want to show that the flow. So I already showed that the flow converges. That means the potential phi t here converges exponential fast in the ample locus of Kx. So I will define this later to the unique singularity Kähler-Einstein matrix in the canonical class Kx. So it should be the weak versions of the result of cow. In the case of Kx is ample, and also the result of Chuzi as well. But of course, I must to prove the convergence results in the weak sense. I mean viscosity sense. Okay. So
please give definition. I don't know what means that viscosity.
Of course, I say that I mean mention the viscosity in the next slides. But here I would like to state, I emphasize that viscosity that means weak sense. Okay. And now we start with some setting before to the viscosity approach. I would like to give some setting on the positivities on compact Kähler manifold. So here less x omega is a compact Kähler manifold, and take alpha is a 1-1 cohomology class in the Dombo cohomology class 1-1 H11, and we say that alpha is pseudo-effective. It can be represented by a closed positive 1-1 current. So that means the current. That means we can define the current is a generalization of forms, in which the coefficients is defined by the distribution sense. Okay, so it's very short. Like this, you can imagine it should be some forms, special coefficients. Here's alpha is called big if the current T can be chosen to be strictly positive. That means T should be bigger than some epsilon times omega. Omega is Kähler matrix. And alpha is nef. That means it lies on the closure of the Kähler cone. So as I explained in the last slide. And here we say that a current has analytic singularities if it can write down locally as a DDC, so IDD bar of some potential, some function U, such that U is sum of the log of some modular of holomorphic functions plus some smooth function. Okay, so here you can see that the singularity should develop inside the intersection of 0 point of fz, when fz is holomorphic function. So it's going to analytic singularities because the singularity developed from holomorphic functions. And the last definition for the cohomology class alpha is ample locus of alpha. So I just mentioned in the last slide definition as the term of ample locus. So here is the definition. So the ample locus of alpha is a set of on X in the manifold, such that we can find a strictly positive current with singularity. So something like this, such that this current is smooth in a neighborhood of this point X. I mean, ample locus is the open Zariski set, such that the alpha looks like a Kähler class in this set. Okay, so in particular, when alpha is a Kähler class, not only big, but it's Kähler class, this ample locus is exactly on the manifold. Okay for this part. So that's it. The definition for the positivity for 1-1 class in compact Kähler manifold. And then now we turn out to our setting for the Kähler-Ricci flow, and our main result is that the manifold X omega is a Kähler manifold with Kx is big. Okay, that means the first class, class, cohomology class of Kx is big, as the definition above. Okay, so we can say that it's a variety of zero type if you want. And then we take a representation of C1Kx, which is a smooth 1-1 form. So theta don't need to be positive because this class is only big, not Kähler. So we can choose a theta is smooth 1-1 form, but cannot suppose that theta is positive. And then we can define the for theta here, we can define the theta Poulry subharmonic function. I mean, PHK is short term for Poulry subharmonic functions. So phi is a theta Poulry subharmonic function if locally phi, so sorry, it's not U, but phi. Phi can write out locally by a sum of smooth function plus one Poulry subharmonic functions, and satisfy this positivity condition in the weak sense of currents. So here, you want to see that if, so for example, theta is a Kähler forms. So this condition to say that we have another semi-positive, smooth semi-positive forms in Kähler manifold. Okay, so but in zero, the theta is not Kähler, so this in the weak sense occurrence. So we can we will denote PHK x theta for the set of all theta PHK functions. So all function like this. Okay, and we can define another functions in this class of PHK function, special function. Sorry, in this class of PHK functions, the supermums of all PHK functions, theta PHK function, such that the supernorm of this function is less than 0. This is called the upper envelope of PHK function x theta, and which is a theta PHK function as well. And we say that this has a minimal singularity. That means if you take another function phi in this class, you can see that this function should be less than b theta plus some constant. So it's exactly the definition of minimal singularities. So another notation is the ample locus of C1kx. So fix so ample locus is the set such that the class looks like Kähler class in this set. So we denote it by U, this ample locus. And now we consider the equations, complex Monge-Ampère flow, which is exactly the form of Kähler-Ricci flow when we write out in local coordinate. So theta t is this form. I already defined above, but I recall here. Theta t is the family of one-one forms, smooth one-one form. Xt is the product from the 0t times x. So t here is any term, any positive term. Okay, sorry. And phi here is a function from this set, and this is the unknown function. We must to define. We must to show. Okay. So now from this equation, we can define our viscosity subsolution, supersolution, and in general is called viscosity approach. So before go into the detail, I just mentioned that in the smooth or regular setting, we have the notation of subsolution or supersolution. So that means some solution, some function which satisfies some inequality with respect to the equations. But when this classical definition is not true if you want the solution is not regular but maybe has some singularity. So that means that to define the subsolution and supersolution, we need to add some regularity or add some smooth thing inside to define. So this turns out to the definition of test function. So now next phi is a function, any function from xt to r, such that at this point t0 x0, any point in xt, we have the value of phi t is finite. Because phi t maybe have some values minus infinity, but here we define on some points that this values is finite. And then upper test function for this function at this point is on C12 function. So we need the regularity here. In the neighborhood of this point, such that at this point this function touch the test function. And the function in original function is below the test function. Okay, so somehow like the upper test function is a function above the original function and touch at one point. And then we have another definition in lower test function is the same definition, but instead of the function is the above the function phi, we have this function q, which is below the function phi. Okay. So now we can define the viscosity subsolution. I emphasize that this definition is on our setting. I mean, the setting for the manifold with the canonical bundle, type bundle is big. So now a function phi t from xt to r maybe has some value minus infinity is a viscosity subsolution for the complex Monge-Ampère flow in the last slide is a function which defined on the ample locus time the interval time interval is upper semi-continuous in this set. No, here's the definition of U. And then we have the control from above by the envelope with respect to the theta t here. And the important thing is that at the point t0 is 0, sorry, omega t, it should be ut. Okay, so it should be t0 is 0 in ut. That means u here and t u times 0t. And for any point in the ample locus time 0t, and for any upper test function, so the upper test function is function c1, 2, we have the inequalities here. So again, it's not mu, but omega, so the volume form. Okay. Here you can see that we can define here in the smooth setting, because Q is C2 functions. So we can define DDC of Q like the Hessian of Q. Okay, so this, the left hand side, you can define in the classical setting, and the right hand side is also classical setting. So this test function allow us to test the subsolution properties with respect to classical sense, because of the function phi here is just upper semi-continuous. So we can, at the beginning, you cannot define the DDC of this function in the classical sense. So we need some test function for determine the subsolution inequality here. Okay, for this point. And of course, if the function phi here, if the ample locus is x, if the k is ample, u is x, so theta is a Kähler form. So the function phi may be smooth. So this inequality for the function phi should imply that the function phi is a subsolution in classical sense. Now for the subsolution, so that means we have the lower symmetric continuous on the ample locus, the lower control for the potential for the function, and in particular the inequalities for the subsolution. I mean, we change the inequality, instead of bigger than, we have less than here. And here, because the left hand side is positive, so somehow the right side is positive, and somehow the left hand side may be negative. So we can remove the part, negative part, by take plus here. I mean, plus omega plus is omega positive, semi-positive, and 0 is otherwise. So here, of course, if this term is negative, this always true, and then just we can check this condition on the positive part.
That may I ask you that the notion of viscosity solution of super solution was introduced by whom in which context?
I will say to it later in
okay,
just few minutes. Yeah, of course I will mention some guys, some mathematicians on this case, and next, viscosity solution is in fact last thing, but is exactly a function which is a subsolution and supersolution. Okay. In particular, you can see that because we control the upper bound and lower bound with respect to the envelope. So if a function phi is a viscosity solution, it should have the same singularity with the upper envelope. So I mean with minimum singularities. Okay. So remark in the real setting on the domain in Rn, the setting of viscosity solution is well known. So I should ask some name here. So the name is Grandant Pierre-Louis Lyon in the 90, and also Evans, Laurent Evans in 90 as well. So is the name of someone who defines the viscosity solution when they try to study the Hamilton-Jacobi equations in the real case, I mean in the real domain. And then in the complex setting, this setting already developed recently by Espicier, Gage, and Zariski in several work in the complex Monge-Ampère flow. But before that, they already developed this theory for elliptic Monge-Ampère equation as well. And in particular, they developed for the case when the class theta t here is semi-positive. Okay, but I mean in our setting, theta t will not have some nice property like semi-positive, but it's just one form. So I mean in my setting, it should be it should be weaker condition for theta t. Okay, so it is some mathematicians on this direction. So of course, in the real setting, we can see some viscosity approach for the Riemannian manifold as well, but I don't want to say in detail here, but I just want to mention the mathematicians we have developed at the beginning is Grandin, Pierre-Louis Lyon, and Evans. Okay. So the key points for the viscosity approach and also for the classical super-solution and subsolution as well is a comparison principle. So simply is that if you have subsolution, if you have a super-solution, and we could say that the subsolution would be less than the super-solution. Okay, so it's the idea of comparisons principle. And in this case, the result is that if we have a viscosity subsolution phi and super solution psi for this Monge-Ampère complex Monge-Ampère flow, and then we have this inequalities. That means the maximum point values of the difference from phi minus size is less than the maximum 0 and supermum of phi minus psi on the boundary at the initial time. I mean, if at the beginning when t equals to 0, phi t is less than psi t, so we can imply that the sub-solution is less than the super-solution. So this exactly what I mean to say about the comparison principle, the key point to prove the existence of viscosity solutions. Okay.
Just a moment. What is the how to say star here?
Star here is upper semi-continuous envelope.
Okay.
Okay. Yeah. So thank you for the question. And here. Now we come to the strategy of our proof for the main theorem. I mean the first result for the existence of viscosity solution for the Kähler-Ricci flow. To show the Cauchy problem, I mean the Monge-Ampère equation with initial condition 0. So I just call the Cauchy problem because we have a condition, initial condition here. To solving this equation, I mean to show that there exists a solution, we need to construct the viscosity subsolution and super solutions. Second step is the well-known or very famous method, so-called Perron method, to get the solution. So once we have a subsolution and super solution, you can take the supermum of all subsolution of the Cauchy problem. So CP. So sorry, we have no 2 here, but CP. This problem. Or we take the supermum of all subsolution of this problem, such that this solution is bigger than the viscosity subsolution in step 1 and less than the super solution in step 1. Okay, so we have the upper bound and the lower bound, and we take the supermode of own subsolution inside this bound. And then we take the upper and lower semi-continuous envelope for phi in UT. So you always the ample locus. And then using the comparison principle, of course, we need an extra argument, but I want to say simply that using the comparison principle, we can say that because we can show that phi star up star is subsolution as well, and phi lower star is a super solution for this CT, this Cauchy problem. And then using the comparison principle, we can show that, okay, so these two functions should be the same. That means the function phi should be continuous and in UT, and which is a solution for the Cauchy problem. So that is the main strategy for to showing that there exists a viscosity solution for the Cauchy problem. The first step is construction of subsolution and super solution. The second step is using a theorem method to find the solution using the envelope. Okay, so this is a strategy. And now I would like to say some point how to define subsolution. I mean viscosity subsolution. And here, because theta is a presentation of a big class, big homology class, so by the result of domain, we can see that rho there exists rho a function with analytic singularities satisfying these inequalities. I mean that the current theta plus TDC of rho is a positive, strictly positive current, and the potential has a normalization supermode is 0. So this is a classical result implied from the result domain on regularization of Kähler current. And then we set the function utx is 1 minus t rho plus ft minus at. So the constant at will be chosen later. And the function ft is the English solution of this ODE equations. So I will say why we choose this equation. The first condition need to be checked is that u is a PLA function. I mean theta PLA function. If you take theta t plus DDC of u, you can see that with u like this. When you take DDC, the term of depending on t will be removed. And then we have the first term is positive term. The second term is positive as well because of the first condition. So we have this function u is a theta PLA function. So here we take the mass, the motion pair mass for this current, one current, and you can see that using the concavity of the determinant, we can see that this will be bigger than this term, and because of theta plus DDC of rho is bigger than epsilon omega 0, so this bigger than this term, because of this bigger than epsilon omega 0, sorry, it should be omega 0 here, and then we take this term on the log, the power of log e to power n log 1 minus e to power minus t. So here we can see that when we take the derivative of u with respect to t plus u, this will appear the term phi t plus phi t bar. I mean phi t plus phi t prime, the derivative of phi, the derivative of the function f, ft prime plus ft, when you take this sum, right? So because this is equal to this term, so is it exactly the coefficient on the exponent here, and log of 1 minus e to minus t is exactly the sum of ft plus ft prime, and then we can see that this is exactly this sum. and here the constant A is here. The constant C appears because of the inequality C and omega. The fixed smooth volume form should be less than the volume form with respect to the Kähler matrix omega 0 n. So it should be omega 0 n. Okay, the fixed Kähler matrix. And then now if you choose A is a log, so here I just say that A should be chosen later, and here is exactly how to choose A. We take A is a minus of log epsilon C here, so we can see that from this inequality we see that we have the inequality for the subsolution. So here this inequality is right out in the pluripotential sense, but by a lemma, you can see that if it choose for the theta t PHK function which satisfies this kind of inequality, the function u should be a subsolution in the viscosity sense. Okay, so I skip the this lemma. So it's basically if you have some inequality in the quicksand of pluripotential theory, you can have this inequality in the viscosity sense. Okay, so I skip this lemma for the moment for this talk. And then the second ingredient is how to construct a super-solution. And I must to invoke the famous result of Xing-Tung-Zhao for the existence of a solution, smooth solution for the complex Monge-Ampère equation in Kähler class, in Kähler manifold with Kähler class. Now, because theta is a representation of C1kx, so it's the first class of canonical class. It is smooth on compact manifold, so we can find some constant A uniform, which is satisfies this inequality, and then we can show the Monge-Ampère equations omega 0 plus ddc of size to power n equal to c times the volume form, our fixed volume form, and such that the function psi is positive. And here is very famous result by Xing-Tung-Zhao, is 78. And of course the function phi here is smooth. Now we take the function v equal to at times phi plus bt. Here at is write down like this. A is defined by this condition, and then with this function v, we can see that the Monge-Ampère operator, Monge-Ampère measures, in this case smooth, so we should be Monge-Ampère volume form, is less than this term, and from this equation and from the definition of at. Okay, so this equation we have that, but here we have a coefficient for omega t, and v we have a coefficient at as well for the phi, the solution. So you can see that it should be appear like the at to power n times this term, and this term is basically is equal to c to the volume form omega, smooth omega. So this should be equal to this term. Okay, so small c is a quotient of two masses, and at is this basically is this function depending on t. And now basically you can choose b equal to log c plus n max log at. You can see that in fact from this inequality we see that this volume form less than this volume form. So that means I say that from this inequality from pluripotential theory, we can see that in fact B is a viscosity subsolution for the Cauchy problem we are working on. Okay, so this idea, a simple idea for constructing of a subsolution and super solution in the case when the class theta here is not Kähler, but in big class we have now the condition, the positivity condition for theta. And the second part of my main result is the convergence of the Kähler-Ricci flow in weak sense. So so we have 5 minutes. So I would say state the result and then the main idea for the result. And let's say x omega 0 is Kähler manifold 0 type as above, theta as above as well. So from the work of Espedier, Regeria and also Espedier, Regeria, Boxon, and Bergman, they show that there exists a unique singular Kähler-Einstein matrix, which in fact satisfies these equations. Okay, so for theta t defined as last time, we can see that in fact the solution of our flow, the normalization, normalized Kähler-Ricci flow, will converge exponential fast in the ample locus to the potential of Kähler-Einstein matrix as t tends to the infinity. So that means this equation is the steady equation of our flow. Okay, so you see that if you remove the term derivative of phi t, it should be somehow the elliptic equation. And then basically our results state that we can detect the Kähler-Einstein matrix using our viscosity solutions. And the idea proof is that using, so we need the existence of phi Ke here, the Kähler-Einstein potential. So using this potential, we can construct subsolution and super-solutions, and using comparison principle to imply that, in fact, we have the difference from two, the potential of the solution. So it should be phi t, sorry, it should be the solution. The minus the fixed Kähler-Einstein matrix potential, Kähler-Einstein potential, it should be less than c to power minus t. So when t tends to the infinity, it tends to 0 uniformly in the ample locus. Okay, so exactly the second part of my result on the convergence of the Kähler-Ricci flows in weak sense, viscosity sense. And thank you very much for your attention.
Thank you very much. Yes, that's very impressive work. Yeah.
Thank you.
So that so you say that why is you say that convergence in open Zariski set where is this condition appear here?
The condition, sorry.
You say that the solution converges on Zariski open subset of the manifold. So why that condition appear here? I mean that's a maybe that kind of general estimation, but a general estimation that is an open set, but either Zariski open subset in the theorem, right? Theorem that's a
yeah. Because in this set the function it should be continuous and the value of this potential should be finite, and then we can compare the difference from two function in the finite in this set, but yeah. Outside this set the function maybe phi t maybe have some similarity.
I see. So that locus you say from beginning. Yes, I forgot. Yeah. Yeah. Thank you. Thank you.
Thanks for the question.
Yeah. So somebody has some any more question to the talk? If not, actually that's very interesting, and maybe I should talk to you later on. Yeah.
Yeah. Thank you. Thank you.
That's really impressive. Yeah. I also study Ricci flow sometime, and but very kind of for simplicity setting very small thing. But yes. So let us thank the speaker again.
Okay. Thank you very much.